Hi! About a year ago I started to work with FPGAs. Originally, I built a double pulse generator for measuring losses in semiconductors and made a video about it on YouTube. It was so much fun that I tried to decode digital audio signals with this FPGA in my spare time. When I recorded the video for the Behringer Ultranet hack in October 2023, I hadn't originally planned to turn it into a whole YouTube series. But in the fall of 2023, however, an opportunity arose to take the FPGA audio mixer presented in the last video to a whole new power level. Every year the IEEE organizes an international student competition with different topics, in which our university wanted to participate this time. For me, this was a unique opportunity to put my existing FPGA logic to a good use. In today's video, I'd like to take you on a partly bumpy journey to a fully digital Class-D amplifier. Before we really get started, let's give you a bit more context. The IEEE organizes an annual student competition with changing topics. The International Future Energy Challenge, or in short, IFEC. In the past, students built a PV inverter, a charger for electromobility or an electronic AC transformer. This time, the students had to build a Class-D amplifier with outstanding features. Class-D amplifiers have been around for many years, but there are still many challenges in the details. In the last video, I showed how to implement an equalizer, a noise gate and a compressor in an FPGA. What would be more obvious than adding a power amplifier to the whole thing? Together with the students, we agreed on a fully digital Class-D power amplifier, which is, however, rather unusual. Conventional Class-D amplifiers used an analog intermediate section and a standard pulse width modulation with switching frequencies of several hundred kHz. As I had already gained some experience with the FPGA, the students were looking for solutions to control a power amplifier directly from the FPGA pin. The obvious choice was to use fast-switching gallium nitride semiconductors in order to keep switching losses as low as possible. The IEEE specifications defined an input voltage of 48 volts, so we opted for 100 volt devices. But let's go back a few steps. In one of the last videos I showed how I used a pulse density modulation with a 1-bit Sigma-Delta converter to generate an analog signal with a digital FPGA pin and a simple RC filter. This gives you an almost unlimited number of analog audio outputs with sufficient quality. However, such an FPGA pin can output a maximum of 40 mA, which at 3.3 volt only results in approximately 130 mW. This is completely sufficient for a line level, but not for a larger speaker. Fortunately, there are many ways to amplify digital signals. The simplest is a transistor stage. But since we wanted to have a bipolar analog signal at the output later on, we simply used the basic concept that makes every motor turn or supplies solar energy to the power grid. A single-phase inverter. As already mentioned, we wanted to use gallium nitride switches, which we simply used in an H-bridge configuration. If the PDM signals then switch to the semiconductors as a gate signal, audio signals can be amplified via a suitable filter. Let's take a look at this in the simulation. As the value range for our input signal, we allow values between -1 and +1. If our signal is 0, we have the highest frequency at the output of the PDM. In this case around 5 MHz, as the pulse density is at minimum. If we change the signal towards a positive value, the pulse density increases, which also reduces the switching frequency, which also has a beneficial effect on the switching losses. If we then apply this clocked 48 volt signal to an LC filter, we can create an analog signal that is also suitable for loudspeakers. We use a coil with a few microhenries and a capacitor of around 100 microfarad in order to achieve a cutoff in the range of 20 to 30 kHz. This looks quite good in principle. For the IFEC finals in July, we then agreed on a modular concept so that we could replace individual boards in case of a fault. The students therefore designed a total of 3 different boards: a control board, a power distribution board and an amplifier board with gallium nitride semiconductors for a single channel each. We used the Arduino VIDAR 4000 board for a first laboratory sample in February. However, As the 2 MB of the small ESP32 within the 9er module, the FPGA and the number of available pins to the SAMD21 were not enough for us. One of the students designed his own control board with a total of 3 audio ADCs, a new ESP32S3, a larger FPGA, the SAMD21 and other functions. So in short, he created a Weide 4000 Plus board. As the design of the circuit diagram with all the additional components, such as the audio preamp and power supply, understandably took quite a long time, the time for placing the components and routing was very short. On June the 21st, the circuit diagram was finished and we were able to start routing the PCB. I then spent the whole weekend with one of the students working on the circuit board and sent it off for manufacturing on the following Monday. Finally, all circuit boards arrived on 1st of July, but see for yourself.
Hey, welcome at the University of Kassel and the Department of Power Electronics. It's Monday the 1st of July and today our PCBs arrived here. We have all components there and we are starting soldering in a couple of hours. I'm right ahead of the lab and then we will see if everything is working fine or if we have a lot of work to do. And I hope everything is going well so that we can fly to the USA at 11th of July. And then, yeah, we will see if we can compete with the other teams.
First we checked the boards for short circuits due to a possible design flaw, but all the boards seemed to work fine. We had a total of 10 circuit boards to assemble, as we wanted to take 2 complete amplifiers with us to the USA. From experience at previous competitions, we knew that there was a chance of damaging the amplifiers during the planned power tests. Then we prepared to assemble the components. To do this, the stencil had to be placed exactly on the PCB so that the solder paste would only reach the desired areas. The solder paste was then spread with a squeegee. In case you've ever wondered what electrical engineers read, resistor books. We had to pay particular attention to the placement of the gallium nitride semiconductors on the board because of the cooling. Due to the large number of components, it took a few hours to assemble them. We prepared 2 boards for the soldering process at the same time. The soldering itself only took a few minutes. We first preheated the boards and then brought them up to the soldering temperature for a few seconds. Overall, the first day was very successful and we were able to complete 2 amplifier boards.
So it's the 2nd of July and the 2nd day of our construction and we finished 2 PCBs for our power stage and 3 more PCBs are following up today and tomorrow, I guess. It's the control board and the power distribution board and 1 more power stage board. So it's a lot of work to do. But let me show you what we did in the last couple of months. The students constructed this PCB here. It's a Class-D amplifier with 3 channels with each 135 watt, based on gallium nitride devices, controlled by the Weide 4000 here. You can see it here. The SD card is there, the audio inputs are there. It's based on an PCM1822 ADC. You can see there the very small, tiny little chip there. We are trying to put this large PCB board into below 1 liter housing. So it's quite challenging to get this size down, but I think we can make it. But let's see what we did in the semifinals in LA and Long Beach. And you can have a look in the short video clip here.
Thank you for inviting us to the semifinals here in Long Beach. We are the flybacks from the University of Kassel in Germany. And now we're going to present our concept for the audio amplifier. Here you can see our full-bridge Class-D amplifier on the left side. We have a filter there and of course a speaker. We're using a 6 ohm. So let's have a look on our hardware. We wanted to build up the first prototype. And here you can see rendered 3D images from the PCB with all parts together. So last week we built it up and here you can see a final picture of it. And keeping these colors in mind, we have now our bill of material for our first prototype. And with all parts together, we ended up at a price of approximately $650 per amplifier, which is quite a lot for an amplifier, but it's our first try.
On the second day, we first soldered the power distribution PCB. Then it was time for the control board. This board in particular has many components with very little space between the pins. We provided a total of 3 stereo ADCs so that we could measure the output voltage for the control loop in addition to the analog audio. As with the prototype, we used the PCM1822 ADC with I2S output. To be able to measure the 48 volt output voltage, we designed a suitable op-amp circuit that measures the output voltage differentially, reduces it to an ADC optimized voltage and also routes it differentially to the ADCs. Assembling the control board then took even longer than the power boards. As only one student was able to work here, the others put parts of the power boards into operation in the meantime. As the high side of a half bridge must be galvanically isolated from other voltages and we wanted to work with steep signal edges, we designed a separate series resonance converter for each gate to reduce costs. This required individual cores to be wound and connected. Finally, we were able to put the control board into the reflow oven. And fortunately, we had hardly any soldering problems, so that we had a finished control board with only minor improvements.
Yeah, well, day 2 is over, but we have finished our construction. All PCBs are soldered and tomorrow we will see if it is working or not. So, good night.
From Wikipedia, the free encyclopedia. The overconfidence effect is a well-established bias in which a person's subjective confidence in their judgments is reliably greater than the objective accuracy of those judgments, especially when confidence is relatively high.
Well, it's already Wednesday night and the day has practically flown by. We wanted to put the control board into operation this morning and unfortunately we noticed something that could be a real showstopper. The students have made their own control board based on the VIDAR 4000 and the board with 4 PCB layers is a great achievement and the circuit diagram makes a very good impression. We had just successfully flashed the SAMD with the Arduino bootloader via the serial wire debug interface, so we also wanted to check whether we could communicate with the FPGA via JTAG or not, but during the upload this happened. So we are unable to complete the upload of the program. We looked for the reason why we could not upload the entire bitstream and tried different bootloaders, as someone at GitHub issued some problems and suggested to try a specific version of the bootloader, but it did not work. The documentation of the VIDAR 4000 bootloader is not very detailed, and I then boxed my way through the code and found this. In short, the Arduino bootloader not only flashes the SAMD, but also the external SPI-Flash of the VIDAR 4000, which we have not taken into account. It has to be said that we only had a few days for the board. Now I'm sitting here for hours searching for a solution to upload the bitstream to the FPGA, and it is very difficult to access the pins of the FPGA, so we connected the SPI-Flash to the SAMD. A few hours ago I wrote software that writes the bitstream from Quartus to the SPI-Flash via USB so that we can use the JTAG between the SAMD and Cyclone 10 to program the FPGA after booting, but that doesn't work yet and I'm pretty much down. Our flight to Austin departs in 190 hours, so time for some sleep, but then I have to find a solution. I have a little hope. I have just found a port of the official USB Blaster JTAG adapter for the SAMD on GitHub. Unfortunately, we missed to route the FPGA's JTAG contacts to a pin header, but we have them on the SAMD. Maybe we can rewrite our code so that we can configure the FPGA via USB through the SAMD directly from Quartus. Tomorrow that will be the first thing I will do, but for now, good night. Well, a control board like this is pretty complex and I'm still annoyed that we didn't just put the flash on it. But I never questioned the fact that the bitstream doesn't fit into the SMD21. Kudos to the guys from the Arduino team who managed to make a complex system with multiple memories very easy to use. But luckily the USB Blaster emulation compiled flawlessly, although a lot of warnings even about blue screens were given in the project repository. In the end, we were able to send our bitstream directly from Quartus via the USB JTAG emulation into the FPGA through the SAMD21. After a delay of almost 2 days, we were finally able to continue with the commissioning of the entire system. It quickly became apparent that we had not designed some of the voltage rails to be sufficiently robust. The 1.2 volt and 2.5 volts for the FPGA in particular had some problems, so we had to install more powerful voltage converters here. Together with a few additional capacitors, we finally had the power supply under control by the end of the day. On Friday, we finally made an attempt to get sound from our final demonstrator. First we tested a few sine waves, but then we couldn't wait to send real audio files to the power amplifier.
Yes, yes, yes!
Oh yes, the first sounds were a load off our minds. Unfortunately, the measurements with the thermal camera showed that we had to expect relatively high losses, especially with our gate voltage supplies using Zener diodes. I then used the weekend to completely rewrite the audio playback and the web server. We had noticed that the higher DVDT on the gallium nitride semiconductors was interfering with the SD card. We couldn't use the originally planned microSD holder because the used footprint had a bug. Instead, we soldered a microSD adapter directly to the ESP32. But due to EMI, we could not use the SPI bus with 60 MHz. Even at 12 MHz, we still had problems. So I rewrote the entire code so that we could use the ESP32's internal flash for the web server and some MP3 files. I also found a few bugs and corrected them. In the end, this took the whole weekend.
The next Monday is there, and at the weekend we achieved a lot. The system is working now, and here is the result of a lot of hours working on microcontroller and FPGA systems. The menu structure is working. The FPGA has its logic. The ESP is working, and our control, yeah, it's working. Yeah, and now we have to put everything together and then see if it is working. And the final measurements we have to do and see if the THD plus N is okay, and then our flight goes to Austin on Wednesday.
We didn't have much time left and still had a lot of work to do. Not all the power boards had been assembled yet, and the transformers for the SRCs weren't ready either. As everyone else was busy, I did a bit of redesigning on our case.
It is Monday evening and all 3 power modules are working and the control board is working too. Here's our controller. I will send the parameters and I enable the amplifier and let me call music file. Hey, and we have sound. Woo, it's really good that this is working now. We have 2 days left for the power tests and for the THD+N tests, and we still have to manufacture 2 housings. So a lot of things to do, but the most important thing is the circuit is working and we can achieve sound here. I'm really glad. So let's see what we can do on Tuesday and on Wednesday, and then we have to pack everything together and then the flight will start.
We still had a lot to do on Tuesday. The housing parts were finished overnight and we were able to continue with the assembly. Many details on the individual circuit boards were still not quite finished, such as the assembly of the display. Over the course of the day, however, more and more came together so that we were able to assemble the first of the 2 superstructures in the early afternoon. However, the connections on the front alone took a lot of time. We then used sound generators to test all the circuit boards again and check the cooling of the semiconductor chips. As we cool the chips through the PCB, we had to check each individual chip with a thermal camera. We also recorded raw data for a later THD+N measurement. On the last day, we packed spare parts and components for emergency repairs that we would hopefully not need. As we had quite finished the 2 front panels the day before, we still had to connect a few last cables here, but were then finally able to complete the first demonstrator. However, the connections required by the IEEE were a real challenge, both electrical and mechanically. In the end, we were all very satisfied with the result. None of us had studied product design as a minor subject, and so this was our first complex housing. For the fact that we only took a few days to build the housing, it's definitely something to be proud of.
It's Wednesday afternoon and only 12 hours left to the flight to Austin, USA, and we made it! The amplifier is ready! Just in time, everything is working. MP3 playback from the flash, the internal ADCs are working to playback via the XLR plugs, the filters are working, the crossover is working, everything is fine. So, time for a bit of sleep and then it will go to the USA. Yeah! So I'm in the train to Frankfurt to get to the airport and my flight departures at 10 o'clock. And yeah, then we have a couple of days spare time to get our system in place and maybe, I don't hope so, but we have a bit time to repair if something gets broken during the flight. And on Monday our first event will take place, so let me have a look in the schedule. We have to present with a 10-minute presentation what we have done in the last couple of months. On Tuesday we have to take the first main electrical performance test, so we have to show if our amplifier can deliver what it should. And on Wednesday the subjective listening test will take place. And then we have to show that our system is sounding very well. And in the afternoon the committee will come together and do the final ranking. And in the afternoon or evening the award banquet will take place, and I hope that we will get a high ranking here. So first, get to the airport.
Okay, border control check. Let's hope that the flight is on time. See you later.
After 2 weeks of work, we took some time off on Friday and Saturday and went on a tour of the Johnson Space Center in Houston. We then used Sunday to prepare for the required presentation. It's always amazing how much time a presentation takes to prepare. Here you can see once again the THDN calculated by us 0.045%. Unfortunately, we made a mistake in the calculation and the value was significantly higher. Compared to German universities, there is more partying on the University of Texas campus. We should take a leaf out of their book, but we still had a presentation to deliver first.
We use an LC filter with combined common mode and differential mode filter. And you can see the parameters in the table.
Yeah, you can see, you can set the crossover, still normal volume controls, you can set the song. You will also see in a moment with the equalizers, the frequency slider is logarithmically, so you can really set the low frequencies well. And over there we have the presets, that's right now flat, breezy, and power, and yeah, there's a noise gate. You really have a lot of options to customize for these audio processing.
And now, here it is. A mission accomplished. Thanks for your attention. Any questions?
We then spent the rest of the morning getting an introduction to precision audio measurement devices. These devices can be used to record and graphically display the voltage and current, power and THDN+N, as well as the frequency responses for several channels. During the tests with our amplifier, however, we quickly realized that our THDN was not less than 0.1% as we hoped, but rather 2%. We didn't have enough time in Kassel to put the controller into operation, so we tried to get the control loop to work under great time pressure in order to reduce the TH+N. Unfortunately, we did not succeed. With a somewhat queasy feeling, we finally had to start the electrical tests on Tuesday. First up was the efficiency test. However, we already knew that the efficiency would not be very good due to our high losses at the Zener diodes. Unfortunately, we didn't have enough time to develop a better circuit during commissioning. Overall, the efficiency was then a meager 72% at full load on a single channel. However, the other two channels also produced the same losses in this test, even we are not using them. The THD+N measurements then produced the results expected on Monday, 2% over a wide frequency range. At least we were able to keep this value fairly stable, but the mood was still very subdued, as the other teams had extremely low values. However, we were then able to show off with a crossover. We were able to demonstrate the functionality of our Linkwitz-Riley-Crossover, which was set to 200 Hz for the test with an IDEA response. After all, we were able to complete all electrical tests without any damage. On Wednesday, the final test was due, the acoustic listening test. We were able to use a lab at the Butler School of Music for this. All teams set up their amplifiers one after the other and had the acoustic properties of the amplifier assessed by a jury in a 15-minute test. After connecting all the electrical cables and adjusting the level to a reference volume, the test began. Unfortunately, we were not allowed to configure our EQs, so the sound was a little flat. But at least our amplifier worked. Not perfectly due to the THD value, but we didn't make a complete fool of ourselves.
Okay, that's it. The official rankings are published and we made place 6 of 7, but the 7th team has no working amplifier, so it's out of the ranking. And yeah, the lesson learned, we cannot compete with amplifiers, Class-D amplifiers with an active loopback. And we have a loopback but not active. So this is the first task in Germany to get this bug fixed and to enable the control loop. And then I will remeasure the THD plus N and see which levels we could achieve with a working control loop. So the project is over. It's done here in Texas. Anyway, I enjoyed this day here in Austin and Houston, and it was a great opportunity to see the town. You see the capital in my back. It's great to get the chance to travel around the world for this kind of project, and I think the students learned a lot. And yeah, we'll see what the culprit for this problem is and see where we could have stayed in comparison to the other teams.
On the way home, I had some time at the airport and developed a PWM with 1.5 MHz audio upsampling, which allows a maximum resolution of 6 bits with a 200 MHz clock. To further increase the signal quality, I connected a Sigma-Delta converter with noise shaping upstream to downsample the 24-bit audio data with 1.5 MHz to 6 bits. Without control, I was able to reduce the THD by a factor of 10 to 0.25% from a standing start. The acoustic quality was also improved considerably, unfortunately a few days too late. I also managed to get the control to work. Using a 100 MHz clock rate was too slow to decode the 12 MHz I2S stream. For now, however, the project is finished and maybe a student would like to write his project work with us and reduce the THD plus N to below 0.001%? Send me an email or leave a comment under the video. So that's for now and see you next time.
Something has to make you run. I don't know why I didn't call. My feel as empty as a drum. I don't know why I didn't call. I don't know why I didn't call. I don't know why I didn't come.